Uh, Today I'm about to talk about riding the wave, which is about creating waveforms inside r2. This is making music. And, well, what are the use cases for r2? r2 is a very versatile tool. You can do so many things. You can reverse engineer binaries, you can debug programs, you can do forensic analysis on memory, on disk, etc. It was originally designed to be a forensic tool, but it has been evolving depending on the needs and my personal fun. And the thing is that it has been extending, adding support for static and dynamic analysis, adding support for debugging, and data and code visualization, scripting, the compilation, and being used as a backend for other tools, having different UIs, etc. But there is still something that I didn't explore yet, which is making music. So I'm not a musician, this is the disclaimer. So I've been learning all that stuff a few months before starting the conference. So I was just trying to have some free time to play with this and implement the thing. So what's a wave? As long as we all like to mess with bytes and hexadecimal values, I wanted to understand how the music is encoded in data. So, and I also like a lot of chiptune music, and I like chiptune music trackers and other software for making music, which is, if you look at them, it seems so similar to an hexadecimal editor. So I wanted to play a little bit with them and try to make r2 a front end for making electronic music. So I started tweaking a little bit r2 to have a UI for having like a kind of tracker. And the thing is that we just stick to just make music. It's in r2 a framework, a reverse engineering framework. So we can provide other tools, not just for making music, but also for reverse engineering music or audio or any other kind of wave, which can be electromagnetic wave or any other kind of signal. So we can use r2 for parsing, doing reverse steganography. We can use that for parse music and understand the file format if there is like, or represent binary as music. And also, I wanted to improve the visualization to have like some comments to print in ASCII art all the waves forms that we are generating with other tools or with other. So let's talk a little bit about what's a sound chip and how do they work. We can think them as coprocessors, so they are like chips that are, can be communicated from the CPU. There are different ways for using them. So we can start thinking about PC speaker, which is the simplest way for making music, which is like a simple speaker that you can say, okay, I want to play that frequency for that time and at that volume, and that will play. But how do you represent volume? How do you represent frequency? How do you represent a specific kind of wave? And I bet that everybody have tried at least once to do cat dep random or cat dep SDA into the dep DSP, at least people from the 19th. And you know how a hard drive sounds, you know how a modem sounds. So let's understand how this thing works. So we can create music, we can make demo scene, we can make electronic music, chiptune, and mainly for artistic purposes. In r2, there is a RASM command line tool, which allows you to assemble programs or assemble small snippets of programs. So I will show you a small assembly program that is used for playing the PC speaker audio. And I'm assembling this small program using RASM2, and we'll play this program using DOSBox. This is the ASM file. I basically ripped this file from this URL. Just copy-pasting, changing some values to make the example smaller. But the syntax is almost the same. So you can see that RASM2 is able to assemble those programs. If you check the make file, you will see that it's just running RASM2, specifying the architecture, 16 bits, then binary output, so this is a -b and -o to specify the output file, and then -f to specify the input file. So if I do that, I have a speak.com, which is a the small MS-DOS program that I have assembled with this. So I will run DOSBox. I don't know if you can read anything here, but yep. Right, so it's running. It did some noise. It should be working. But anyway, so, sorry? I killed that process. Yeah, I erased it also. That. Yeah, so that was the sound. Okay. Let's continue. You know SID, it's probably one of the most famous chips for making music in Commodore 64. There are still some people using these chips, and there is people selling like boards that you can control them using USB or serial ports, and you have like 4 different SID chips that you can make music with them. There is basically different oscillators. You can create different kind of waves with them. You can apply filters and then create loops, etc. So you have basically a coprocessor that you have ways to using input and output instructions from the control CPU to modify that kind of waves. Also, the music in Game Boy was created in the same way. So it was programmatically inside using Z80 modified Z80 CPU was reading and writing some specific address in memory to modify the behavior of that secondary coprocessor to make that play music. For Game Boy, there is a bunch of, well, there are actually 2 different ROMs, which are not official from Nintendo, but you can buy them online, and they are called LSDJ and Nanoloop. These ROM cartridges work in original Game Boys, but you can also use them in emulators. And they are basically implementing a chiptune tracker using the Game Boy hardware. And you have a UI like this, which is kind of similar. Like if you see this, you will probably think that it's an XML editor, but it's a way to make music. So you can specify the wave noise type, the wave type. You have different oscillators, and you can specify create different instruments, and then apply on a different track each of these instruments with specific modifiers on them. There is also other, this is an open source, the other one for Game Boy are closed source, but there are also open source trackers for NES, for example. This is Milky Tracker, which is a portable tracker for making music and works even on Amiga. So let's see how the waves are encoded in binary. So first we need to specify how the audio device will be handling this data, because modern computers are handling waves, not handling specific changes of configurations in a specific coprocessor of the CPU. I choose Signet 16-bit integers. This means that each value that I will be writing in memory, it's a short, so it's a Signet value. And this signet value will be specifying the y value inside the representation of the wave. And the offset inside the memory will be representing the x axis. So then if we specify mono or stereo, it means that the mono will be one value after the one. And in stereo, we will have like left channel, right channel, left channel, right channel, left channel, right channel. And then if we read all the values, we will see that the wave, how the wave is represented. And then we have the resolution in hertz. And resolution means how fast is this buffer read. And the faster we read, the better quality of sound we have, because there's like more samples per second. So it seems easy, so let's make it a try. We have also to understand what's amplitude. Amplitude is how tall the wave is. So for example, if this is the value of 0, and this will be the signet integer, depending if 16-bit, 8-bit, or 32-bit values. And the taller the wave is, the more volume will sound. So it will be a stronger sound or like not that strong. And the frequency is the distance between them. So if we have like a very close, so the top of the wave is very close, it will be like a high pitch. And if they're like very separated, it's low pitch. So it's like a bass or... Okay, so the graph at the bottom is something that I generated with r2con2018. So that's kind of a spoiler of what you will see. So basically, the way that you represent the data is how you represent these values in memory. I can make a demo if you want. Whoops. I can make a demo about how this data works. So I will open r2con2018 with a malloc of 1 megabyte. 1 megabyte is enough to fit some seconds of music. So, and I will AUI to initialize the audio. So there is the AU command to mess with all the... It's missing the installed step. Okay, so the AU command is the one that exposes all the functionalities for the audio creation. The most important one, at least for starting, is the init audio. So we need to initialize the audio. By default, it takes these arguments, but we can change them. So we can specify like different hertz, or maybe we want like 32-bit or 8-bit and stereo, etc. We'll stick to the false. And right now we have like zeros. There is nothing. We can use AUP to show the wave, which is just one line. But we can use AUW to write a wave. This is all the kind of ways that you can create. So let's create a sinus of 400 hertz. If we show the data, we see that there is a lot of hexadecimal numbers, so it's not 0 right now. So we can use the PXD tool to show this buffer in shortens. So we see that there are like a bunch of numbers, and they're like signet. And if you read them one after the other, you will see that it's like at the beginning it's growing, at the end it's going down, then it's a negative after passing the 0 value, and then it's going up again. So if we use we can clear the screen, and then we can use AUP to print that, and we see a wave. Okay, so we want to know how this sounds. So we will use the AUB command, which is a command to specify the block size for the audio processor. So the reason for that is because the B command is the one that we use in r2con2018 to represent data, and we don't want to watch 1 megabyte in a single screen, otherwise you will not see anything. So we can use like AUB and maybe like 100 kilobytes. And we will write this wave again. You can see that it's in here. And if we use the AU dot, it will basically dump the current block to the sound card. Okay, so that worked. Arpeggio is one of the techniques that is used in Chiptune to exploit the features of the hardware, because as long as there are some limitations and you cannot create so many waves at the same time, because when you have, obviously music is not about making like a piano that you can only play one tone after the other one. There is usually more than one instrument at the same time, so you need to mix the waves to sum the value on each of the points of the x-axis. And then you can basically simulate that there is more than one instrument at the same time. So without mixing, we can use Arpeggio, which means changing the frequency in small period of time. In chiptune music, this is known as blurping. And I have implemented this in the AUE command. Basically, as long as we have AUE, this command accepts as argument is in a list of integer numbers. Each integer number will be adding this value to the original frequency that we are specifying when we are writing a wave. So if we have created a 400 Hertz wave, we want to increment a bunch of different values after that. So we will start with 0, which means 400. Then we will increase 100. This means that this will be 500. We can do something like that. Then we write the sinus again. And if we show this wave, we'll see that that's the same. We can go into visual mode and, oops, wait. Okay, so we specify that we want to specify the want to use the arpeggio effect on top of the sinus, because by default it's not using anything. And then we write the sinus, and then that was the arpeggio on top of that. If we change the size of the wave, that maybe we can use that AUV of 2000, and we write the sinus again. So it's playing in less time. So that's arpeggio. We also want to understand the different kind of waves that we can represent in memory. What we have seen is the sinus, which is the first one that you see in the graph. But there are other kinds of waves, and we want to understand how they sound in order to mix them or use them. So we can also create like a square wave, a triangle, a sawtooth, but there are so many others. I mean, we can take these different and mix them, or we can just shift one after the other and then mix them. So you create like peaks of different waves, or mix them to get the kind of noise that you want. Also, you can create noise. I will explain what's noise after that. So if you have seen, there is the AUW command that allows you to specify that you want a sinus wave. Cosinus wave is just a test, because obviously if you make like a sinus, it's the same as a cosinus, but it's just shifted. But the song, it will sound like the same. So we can utilize the audio, we can create like a, well, the block is fine. Okay, so we can create cosinus, like the same, but we can create a saw, for example, which sounds different. We can create a pulse. We can create noise. There are also interesting kind of waves that you can experiment, like, for example, crosses, which is like two mixed triangles mixed in the middle. This is with K. And you can also create silence, which is basically setting everything to the same value. So you can make silence with 0. You can make silence with 1000, for example. So any kind of value that is not changing is basically creating silence. And we can also create like an incrementing value, so like something like that. Or like a decrementing value, like that. And the pulse, which I didn't show yet, so which is different from the square. Okay, so now that we have understand that different kind of wave, we want to understand what's a tone. When people make music, they used to follow some specific patterns, mainly because they sound right. I mean, the human ear understand them as something that it's good, or it sounds like something beautiful. So some people decided to specify some frequencies to some notes, and I created a piano inside the visual mode. And you can see that basically, you can see that there is C0, C0, dollar, D0, D0, dollar. The dollar thing, you know, the keyboard, there are like the white and the black keys. So the black keys are the ones that with half the dollar, and the black ones are the ones that doesn't have the dollar. So if you check this pattern, which means white, black, white, black, white, white, black, white, black, white, black, white, white, black, and you compare that to a piano, that's the way that the keys are created. So all the music and the notes that we play for making music are following this pattern. So we need to create this array of numbers because each of these notes is associated to one frequency. Correct? So the 400 frequency that we listened before, it is associated with the G4 dollar, approximately. So let's go into visual mode. I'm doing that from scratch all the time to reset settings. And there is a specific visual mode for audio, which is the AUB. If we press the equal key, we get the piano on top. And we can scroll right. And then we can use the numbers as keys. So the funny thing is that we can use the same tones with different kind of waves. So we can play the same frequencies using different waveforms. Using J and K, the up and down Unix keys, you can change the animation on top. You can see that this is the animation that represents the current wave. If you use J, and we can play that. Or and that's with tones. So as I said before, you can compare these numbers. It's in my to-do to buy a MIDI keyboard or play with the iPad to use that as an external keyboard for introducing the MIDI keys into the Router 2 to play the music with real hardware. So the thing is that you can compare that with the keyboard, which is the thing that you saw before. And okay, let's see how this piano thing is written inside Router 2. Using the AUP, it prints the piano. We can use the AUF to print the tones as flags. So we can use the flags as alias for the tones. So we can then script that and create some macros that are changing different tones and make music with that. So just taking any partiture that we have the notes, and then we can use that as using the flags to write the waves in memory. Okay, let's talk about noise. How can we create noise, and which kind of noises we have or we can create? As we saw before, we have the AWS N, to create noise. And the noise, if you write this, with initializing the wavecard, you cannot write anything because it would not sound. I mean, it doesn't know the size of each of these values. So let's write some noise. Yep. We're going to visual. So as you see, the noise is created by basically writing random values in memory. So writing random data creates noise. The thing is that there are different kind of noise. And this is the name of this kind of noise, which is completely random, is called white noise. Finally, there are different colors of noises, and each color is associated to some attributes or some kind of sound. So, for example, the white noise is so random, but as long as they are like more dark, the noises are less random. So, for example, the black noise is similar to the static noise. So it's like silence with some little glitches. There is, for example, the brown noise or the pink noise, which are similar to the, for example, a fountain with water or a snowstorm. But there are many more. There are like red, green, blue, violet, gray, black. You can check this Wikipedia page to understand how these waves are created. But I added support for only 3 of them. So you can create with using AUN. You can use brown noise. Let's change the block size to 1 kilobyte. Well, 1,000. Oops. Okay. Yeah, maybe let's double that. Okay, so that's brown noise. If you can compare that to the white noise, you see it's quite different, but it's still noise. So let's check the pink noise. Okay. So let's see the attributes of this, or how can you exploit this for hacking humans. I don't know if you know about binaurals, but binaurals is a trick that it's basically mixing different kind of noises in different kind of patterns to make the brain adjust the different levels and that way you can, for example, if you can sleep, you can fix your sleep using binaurals, for example. If you can concentrate, you can use that to increase your concentration. And you can also make your baby sleep. And actually, it works. Okay, I will make a demo later on that. So, I don't have babies here. Anybody have a baby here? Sorry. It's just for a demo. So, let's talk about the effects. There are different effects that you can apply to the wave. Some of them can be applied before you create the wave. Some of them can be applied after. So, for example, we can use pitch glitching to change the pitch after over the time. So, depending on the distance from the original point, you can decide that you change the pitch, which means the distance of the waves. But you can also change the amplitude over time. So if you change the amplitude, you can create, for example, like when you press a key, that there is like at the beginning it's like the attack is really high, and then at the end it's like lowering slowly. So you can create this kind of effects using different command. So you saw the Arpeggio command, which is basically changing the pitch over time. But we want to change the amplitude over time, which is changing the volume over time. This can be specified using the AU uppercase N command, using an array of integers, which is basically dividing the full length of the wave by the amount of integers that you're specifying as argument, and then using that to modify the loop that is creating the wave over time. So let's make a small demo. We will use the sinus wave, 400. But we want first to specify that we want to change the amplitude over time, and then we will use, for example, 0, 100. Whoops. Oops. Demo. Ah, no, sorry. AU. Well, that was not expected. But yeah, I mean, it's working progress patch. I mean, I didn't. It was working some days ago, but I was just changing some stuff. I didn't have time to test all these things. When people who makes chiptune music or making music, you have to understand the attack, the decay, sustain, and release. These four concepts are specifying basically. You can check that in this wave. The attack is the time that's starting from 0. From the point that is the maximum number of the value. The decay is after the tone is pressed. And then there's the sustain, which is maintaining the same tone. And then at the end, there is the release, which is like lowering down to silence. So we can create that with a post-processing filter, like I showed before. How can we mix waves? We can use the AUM command, which is used for mixing waves. So you can, for example, create 2 different sinus, which is like 2 different frequencies. And if we sum them, which means that we take the value in this point and we sum the value at this point, and then we create a new value, and etc. So it's basically summing the 2 values and dividing by 2. So it's pretty easy. Let's make a small demo about that. So we create malloc of 1 megabyte. We can create like a flag at 500, like for example the second. So we create a sinus of 400 in here, and a sinus of 800 at second. So now we have this, but if we mix that from second to the current offset, it will be mixing the 2 waves, and you see, that this is the sum of the 2 waves. We can play that. Okay, that's how the mixing 2 waves of 400 and 800 hertz in sinus waveform is sounding. Okay, I will make some practical demos later. So let's design our audio CPU. r2 have a seal, so we can emulate code. We can create our own music programs using a seal. This means that we can take, for example, MIPS, ARM, x86, Z80, to write some code, and we can, for example, implement a syscall handler that when the code is calling an interrupt, it will be configuring, taking the arguments, define it in the registers, and create like a wave. We can also implement a real hardware, so maybe like taking a seed chip and then understanding how it works and implement that on top of a seal, so we can use that to play with that. But that's not fun for me, so I decided to create my own architecture. How this architecture can speak to the outside wall. We can map hardware registers, we can use EO ports, we can use syscalls. We can also create a background main loop. This means that using the ampersand command, we can run a command in background. And we can execute, for example, one command in loop, which will be running same block from memory in loop. So it will be taking the current block, dumping it to the sound card, taking it again, and so on. But meanwhile, this is happening in the visual mode. In the first thread, we can be modifying the memory at runtime. So which kind of questions we can spot or we can think when we are designing a new CPU? We have to decide the register size. This means that if we want to process audio of 32-bit, we have to create a 32-bit CPU. And how many registers do we want? The more registers we have, the easier to write code for it is. We have to specify how the instructions are encoded. We have to specify the endianness of this architecture, and obviously how to specify how we create waves and all the operations that we have created, or I have shown before with comments in r2. So I created a very simple change inside the SEAL virtual machine, which basically implements, if an SEAL expression starts with an exclamation mark, it will be running the r2 command when the instruction is executed. So you can use AHE command, which is basically to create an anal hint for a SEAL, which changes the SEAL expression for the current instruction. When you do that, and you use AO command to see the SEAL expression, you will see that hello world command will be executed. And if you do a step, you will get the output of this command in the shell. Let's make a demo. So we do that. We see that this is the current expression for the push RPP. But if we change the expression to be like this, and we do a step, in visual mode, you can see that. Demo effect. Anyway, the thing is that when we create the architecture, I created r2AO, which is this plugin, and the only dependency is libao, which is a library that runs on Linux, Mac, and Windows. But I was focusing on Linux and Mac. The way libao works is that you have to call AO initialize, then you create, you call AO default driver ID, and then you open the device specifying the options that I showed before, so the rate, bits, channel, and Indian. And then we use AO play with the buffer and length as arguments. So that's pretty easy. At the end, we have to call AO close to close the device, and finally AO shutdown to shut down the library. This is what I showed before. More comments. That's what I explained before. The stranger guy implemented the proper way for using the background comments. This is basically running a thread in background, and you can call r2 comments from the two sides without having like race conditions. So in visual mode, I will show some more tricks for that. So this is the virtual audio CPU that I have created. We can open a 1 megabyte. And if we do the as.arch equals to O, we'll see that there are knobs here. But if we change the values, it's changing the way that the data is represented. So it was the hash. That was when it was working. So the thing is that this is the correct representation. So we can create loops, we can move values to registers, we can move values between registers, we can play the current block, we can change the block size, we can create a new wave of different types, sinus, cos, raw, pulse, noise, etc. And then changing the frequency for each of these waves. And the funny thing is that if we use SEAL, we will see that half of these instructions that are only messing with registers and immediates are represented as standard waves. But the SEAL representation, if it contains a hash and then an ampersand, like a hashbang, it will run this command inside Rudder2. The reason for using this is that at the beginning I implemented only the hashbang, but the thing is that it's easier to use hashtag, because this way the other SEAL emulators or other tools built on top of a SEAL will not collide with this, because the hash character is used to specify comments in the SEAL expressions. So if we go into the visual debugger view, just pressing P again, we will see that there are registers. And this is all the registers that are created inside this virtual machine. So we can just step into and create wave and play audio, etc. More things that we can do in visual mode, just pressing question mark, you get all the help. So you can move around the memory space and visualize the wave. using standard Unix keys like JKHL. We can use the R to randomize the colors. We can assign a specific waveform to one key using the N key. We can use the notes. We can play the notes specified in the piano using the numbers from 0 to 9. Using P, you can rotate between different modes, and then using E, you can change the arpeggio, percent, etc. effects that are applied into the waves that you're creating. So that's all the representations that you have. If I write wave, you will understand better the different representations. So this is, instead of using a wave, we're using progress bars to represent the waves. So each short value is printed as a percentage. And using JK, I'm changing the kind of wave I'm generating. Then we can use the plus and minus keys to increase and decrease the frequency. You can check that value on top of the title of the... And then you can use the divide key to reduce the value for 100 hertz. Okay. So the keyboard is nice, but many people is making music with game consoles, so why not add support for Gamepad? So I added another plugin, which is called Gamepad, and when you run the command got mode on, it will start a visual mode that is reading the input from a Gamepad, and yeah, you can basically inspect or use r2 using a game console. This is fun, but the thing is that if somebody is porting a r2 to any embedded game console, and you only have like arrow keys or buttons to play with or interact with the device, it will be interesting to improve this Gamepad visual mode in order to have like a proper hexadecimal editor using a Gamepad. So now we'll be pressing the keys, so you can go up, go down. We can press the key to change the kind of representation. I will open the standard binary to get like more proper representation. Sorry. So we stick around, we change to this assembly. We can go around. The funny thing is that when you are in hexadecimal view, one of the features of a gamepad is that you can press more than one key at the same time. So you can go up, you can go down, right or left, but you can also go in diagonal, like pressing up and right and down at the same time and things like that. So you can change also, enable the colors, disable them, etc. This is just a demo, but the thing is that there are so many different ways to interact with a gamepad, and it would be cool to have like a proper interface for messing with binaries using these devices. Okay, these will be the bonus demos. So all the theory is done. I don't know if you know how telephone works, but now r2 can be used to call phone numbers. Okay, DTMF stands for this standard, which is basically each of the numbers that you have in a phone is basically a mix of two different frequencies. So the reason for that is because it's pretty difficult to create two waves mixed together by any real sound. So it's easier to process that by a machine and differentiate that from voice or music or any other things that you have in background. So you can see, for example, that when you press 1, you're mixing 697 hertz to the 1209 hertz frequency. So this will basically do what I showed before. So I created a wave, I created another wave, I mixed them, and then I played this buffer. Okay, so let's see this demo. This is the TMF r2 script. I'm initializing the audio card. Then I'm creating a new flag, 3 new flags, which is apps, track 0 and track 1. And then I'm changing the audio block size to the apps value, which is, this will be the length in time represented in bytes of the tone. So how much long will be the keys playing. Then I created a macro, which takes only one argument, which is called tone. And this tone takes the frequency as argument. So it will be seeking to the track 0, writing the frequency, and then playing it. OK, but I don't want to play. I don't want to run only one frequency. I want to mix 2 of them. So I created the phone macro, which is this one, which basically takes 2 arguments. Takes the first frequency and the second frequency. Then it calls AUWS to write a sinus wave at the track 0, then creates the second wave in the track 1. Then it seeks to the first one, and then mixes that data from the second, and then plays that value. OK, so I created new macros that are calling the other macros. So the macro 1, which is the name of the macro, will be calling the phone macro with these 2 frequencies. So if you compare that, that's the 2 frequencies that the phone have in the standard. And I did all these keys. OK, so that's it. That's all the things you need to make a phone. So that's the makefile. It is basically, I'm not doing anything else than just taking the script as argument, interpreting it, use -i, then use -c to change the block size, but that's useless because I'm resetting it in the script, and then AUB to open in visual mode. OK, I'm in visual mode, so I want a phone. This is not a phone. So I will press the exclamation mark, and I have a phone in here. So as long as all phone numbers in movies start with 555, I will start with 555. But I want to play other numbers, like random ones, like 6. So yeah, that's a phone. Let's go to the next demo. This is jam mode. Jam mode is basically what I showed before. It's playing music in real time. We can do that using a background thread that is taking the buffer and flushing it into the sound card all the time. And then we have like a front end that we are changing options or frequencies or changing the tone that we are using in there. If you want, I can make the jam demo again. But it's basically, we go into piano mode. We can scroll the piano to the right. Well, I'm very bad at playing piano with a hardware keyboard. OK, so what else can I show you? There is, we can import music into our memory. So I will take an MP3 and then convert it into WAP, and then we will play it. So this is the makefile, which is basically using FFmpeg, taking this sample file and then creating a WAP. And then I'm using this line to open the file. So I will just do that from scratch. So I will open the file using -end, because I don't want to parse binary headers, because there are no. I will open the WAP file. And I want to change the block size to something big, like maybe 500 kilobytes. Then I want to play that buffer. I want to initialize this first, and then I will play this buffer. Okay, that doesn't sound right. Have to wait now. Well, I can kill this. Okay, let's run again. We'll use a smaller block size. The thing is that we have initialized this buffer with these settings, so I will change that to be 44100. And then we will try again. So we see that at the beginning of the WAP file there is some headers, but as long as I'm playing all together, the header is not really, you will probably not notice this. And after that there are a lot of zeros, so it's silent. And let's play that. So it sounds better. And I want to change another option because this audio was created in stereo. So I want to add stereo 2 channels to this buffer. And then I will play this buffer. Okay, so that's how you print music using r2con. If you make the font size so small, you can scroll around the web and see the different kind of waves that you will see. So if you go into visual mode and you scroll around, oops, we'll change the block size first. Press 3 times. Okay. And we can change the, using the bracket keys, we can change the resolution of what we are seeing. So if we use these bracket keys, we will be representing more data. So it will take like maybe 200 kilobytes from visual mode. And this is how this wave is represented. So we can scroll. We can also scroll like smaller, like 1 byte every byte. So it sounds like it's repeating the same tone because it's not scrolling that faster. But you understand the way it works. So obviously you can use that to import WAP files into different offsets and use that as samples for mixing them and create your tracker or pad file for playing music. Okay, so let's talk about how to make babies sleep. This is done using brown noise, and it works. So the thing is that we'll use the AUN brown to specify that we can create the brown noise. Then we'll specify 1 megabyte, and then we will write the wave in memory. So hopefully nobody will sleep now. And oops. Right. We'll try with a smaller block size. Okay. So that's brown noise. So if you play that for a long time, you will probably fall asleep really fast. I also tried with me, and yeah, it works. In fact, there are so many mobile applications that do the same thing, and you can also saw the brown noise in YouTube videos. So it's easy to rip that from somewhere if you like long wave. And if you want this to work better, I recommend you to use stereo, because if there are like brown noise in 2 different channels, it works better. What else can you do with r2con? I didn't try that. In fact, I think it's kind of pseudoscience, but you can try. I mean, And that's how you do that. So I'm initializing the audio sound card for 44100 in mono. I don't know if it's mosquitoes listening in stereo or mono. You can you can change the block size to 256 and then define an arpeggio, which will be basically creating an arpeggio of a bass frequency. And what the legend says is that mosquitoes don't like higher pitch, and they get really annoyed about that. So if you play a high frequency, don't laugh. Okay, so if you create a an arpeggio with higher frequencies, it will be playing that. And what I'm doing at the end, at the last line, is running AU, which is the current block, for twice. If you prefix a comment in r2 with a number, it will be running this twice. So for example, if you do that, and you run PD1, and you want to run this PD1 twice, you do 2 PD1. Okay? That's kind of useless, but if you do this thing inside a macro, or you do this thing with AU1, AU dot, for example, to play the current block, it will play the current block twice. Okay, so let's run the mosquitoes and any mosquito in the room? Okay. Yeah, that's it. Questions?
So, any questions?
Is it possible if I analyze malware, then the sound came up in the office, stuff like that? Is it possible now?
Yeah, in fact, some people was suggesting me to add support to R2 Wars to make music. So make the R2 Wars competition have like background chiptune music auto-generated from the code that is running in memory. This requires some more time because you need to experiment with that. But I think it will be possible to extract information from binaries and create some kind of patterns out of that and use that with sound. And in fact, I know that there are at least 2 blind users using Braille interface for Radar 2. And I guess that using audio as another input can be useful for them because they can quickly identify different kind of binaries or the shape of a graph, for example, or the complexity of something, just using the ears, so listening.
You won't add the sound effect if a person type PX, it will be blah, something like that, no?
I can't do that.
Oh, yeah, don't.
In fact, there is, I don't know if you know the say command.
Hello.
But this is from Mac command, it says hellscape. But yeah, TTS. If you enable this, and then you print instructions, oops. Oops. Yeah. What? Well, anyway, it was supposed to be working. So it's basically calling the system command to make read the text that is in the screen. So you can, for example, create a script that is printing different stuff from a binary and make that read that for you. So you can just put that while you sleep, so you memorize the binaries, for example. More questions?
Do you plan this plugin to have some MIDI interface connectivity?
Yeah, I don't have any MIDI hardware device at home, but I was thinking in buying one or just using the iPad as an input with GarageBand because there is like a MIDI interface for that. But didn't check the MIDI APIs yet, so I don't know how that works.
Okay, cool. Be happy to test it if you...
Cool. Yeah, I plan to publish all the plugin and so on because that's in a private Git repository, but I will make that public and as well as the r2pm package soon.
Shall we expect a movie player for next year?
Don't spoil my surprises, please. Another question?
Out of curiosity, for how long have you been working on it?
Yeah. Real work is maybe 3 weeks or something like that. But it was expanded to 4 months, something like that. So I didn't have too much time for playing with this. And I was just spending like at 4 a.m. when nobody's annoying you, you can just make noise, brown noise, and other waves at home. And nobody will complain. So I was basically taking some spare time every week or every month to play with that. So maybe if I have been spending full time doing that and learning from scratch and so on, it will be like 3 weeks, something like that.
Okay, thanks.
Any other question? Okay, thanks.